Now next we will see the waveforms of current and voltage that we have also seen in case of series RL and RC circuit. Here this red waveform, sinusoidal signal or waveform, represents the voltage, and this blue dotted waveform represents current. Now this is the case when omega L is more than 1 by omega C. That means the net effect is inductive, and when the net effect is inductive, we know that the current, this current lags corresponding voltage, and that's why we can see here that this is the current which is lagging the corresponding voltage. And waveform wise, how to understand that has already been discussed in the class. And since the net inductive or capacitive effect, whatever, but it will not work as a pure inductive or capacitive circuit, because we have also resistance in that path. That's why the phase difference will not be 90 degree, rather it will be less than 90 degree. If it was 90 degree, then this value would have been 1.57, means where from the waveform of current had started. But since this is around 1, that means this signifies that this is less than definitely 1.57, and the phase difference between voltage and current is less than pi by 2, because 3.14 radian is equal to 180 degree. So it will be when it is 90 degree, it will be around 1.57 radian, but it is around 1, so it says that it is less than 90 degree. And in the next case, where the capacitive effect is more, 1 by omega C is more than omega L, so net effect is capacitive. There again, this is the waveform of the voltage, so, and this is the waveform of the current. So here we are seeing that the current is leading, current is starting before voltage. When the voltage is just starting at this point, at the origin, the current has progressed to a certain extent. Now again, we can see here that this value is around -1, and this is not minus, this is less than minus the value wise, and the mod value wise 1 is less than 1.57. So here if suppose again the phase angle was 90 degree or pi by 2, then this point would have been minus 1.57, the point where from the current waveform had started. But it is again like before, it is less than 1.57, so it proves that the phase angle or phase difference between voltage and current is less than 90 degree, as again in the circuit we have a resistance. So this was the waveform for when the circuit has the effect of the circuit is inductive, and this is the waveform on the net effect of the circuit is capacitive. Now next we will solve a numerical based on series RLC circuit. As the problem statement says that we have a series RLC circuit where the R value is 20 ohm, L value is, the value of the inductance is 200 millihenry, and the value of the capacitance is 500 microfarad. And in that series RLC circuit, we are applying a 220 volt 50 Hz AC voltage. Now this 220 volt, as we know, this is the measurement of RMS value of the voltage. This is not peak value, and there is definitely a relationship between peak and RMS value, and this is the frequency, the linear frequency, small f of the supply. Now based on these values that are provided, we have to obtain the expression of instantaneous current and also voltage drop across each element, means I, VR, VL and VC. Let's start with first I. Now first we can find the inductive reactance, and that is XL will be equal to omega L. Here omega is 2 pi f, and then multiplied by L 2 pi, and pi is 3.14, f is 50 Hz, so 2 pi f will give us 314, and the value of that inductance is 200 millihenry, so 200 multiplied by 10 to the power minus 3, and that will give us finally 62.8 ohm, and as we know the unit of reactance is ohm, like resistance. Now next, if we find the capacitive reactance, then it will be 1 by omega C, so it will be 1 by, again omega is equal to 2 pi f, so that value will be same 314, and then the value of the capacitance, and that is value, that value is 500 microfarad. So 500 and microfarad means 10 to the power minus 6. So now if we simplify this, we will get the value as 6.37 ohm. Now resistance value is already given and we have already obtained the reactances. So based on these three values, we can easily find the impedance of that series RLC circuit, and that will be, as we know, R plus J XL minus, or we can say J omega L minus J divided by omega C. So it will be R has value 20 and the J value, it will be J, and XL or omega L has value 62.8 minus 1 by omega C, and that value is 6.37. Then it will be 20 plus J, 62.8 minus 6.37, that will give us 56.43, this much ohm. This is the impedance value. Now if we express, this is a rectangular format, so this, if we convert this rectangular format to its equivalent polar format, then this value will be 59.87 R value, and then theta value will be tan inverse of this value divided by this resistance value 20. So it will be around 70.5 degree, and this will be, the unit will be ohm. Now from the expression, from the value of impedance, and already the voltage value is given, we can find the value of current, this value, and since this will be V divided by Z, and since this V value has been given in the problem statement as the RMS value, so the current value that we will be getting here, that will be also the RMS current, IRMS. So it will be 220 divided by the Z value, which is 59.87, angle is 70.5 degree. Now this 220 angle, since we are taking this as reference here, so angle can be taken as 0 degree. Simply we'll divide 220 by 59.87, and that value will come as 3.68, and angle wise we'll subtract this value from 0. So finally that angle will be negative angle, 70.5 degrees. This was current, so the unit will be ampere, but this is IRMS. Now we know that the RMS value is peak value divided by root 2, and if we want to represent the current, the instantaneous current value, then in that expression we basically write the peak value of the current or voltage. Here it is current, so we need to get this value Im, and that we can obtain or calculate as this I RMS value multiplied by root 2. So RMS value is this, and finally the peak value will be, it will be 3.68 multiplied by root 2, and that will be 5.2. Angle wise there will be no change, it will be minus 70.5 degree, as this root 2 has only real value. So angle wise, even we think, then that angle will be 0. So angle of this current will be added with that 0 degree, so it will remain that angle only, which itself is negative. So this will be ampere. Now we can easily express the instantaneous current, that will be Im sine and then omega t minus 70.5 degree, and this will be ampere. And current value, here in the expression of current we can see here the phase angle is negative, and voltage, when we took that as reference with respect to that voltage, current, the current has a lagging phase angle. That means current has lagging phase angle means the net effect of that series RLC circuit is inductive. Here the current lags voltage, and from the values of XL and XC, that also from those values also we can conclude that since XL has more value compared to XC, so more effect, or the net effect of the series RLC circuit will be inductive, and that's why in the expression of current we have got lagging phase angle. Now the next thing that we have to obtain is the voltage drop across each element. Now VR we can easily find, because VR, it will be simply the current multiplied by the resistance value, and they will be in the same phase as we already know. So IM, that value is 5.2, and if we multiply it by that value by resistance value 20, then finally it will give us a value like 104, and then it will be sine omega t minus 70.5 degree ampere. And now if we want to find the voltage drop across the inductor, then it will be simply L di dt. Now this can be obtained in two ways. One way is this phase angle we obtained here with respect to the phase angle of the current we obtained here with respect to the voltage that we took as a reference. Between voltage, the net voltage that we applied across the series RLC circuit, and the net current, the phase difference is this minus 70.5 degree. Now if we draw the phasor diagram of this circuit, it will look like this, where I here has been taken as reference. With respect to I, VR has been plotted in the same phase, and VL, the voltage across the inductor, only across the inductor, this will always lead the current by 90-degree phase, and the VC, the voltage drop across capacitor, as we know, that will always lag the corresponding current by again 90-degree. And this green phasor is the phasor of the net voltage, and here we can see this net voltage is leading the corresponding current. Now VR and I we have already expressed and we have already obtained. Now if we want to find out the VL, this can be found like this. Now L di dt, L value is we know it is 200, and then 10 to the power minus 3, 200 millihenry, and it will be next dt, and in place of I we can write 104 sine omega t if we take current as reference. So it will be finally 210 to the power minus 3, and from here we will be getting 104. It will come out as per the rule of differentiation. The net current is 5.2, it is not 104, so 5.2, that means here we will write 5.2 and then omega, which is 314. 2 pi f is again here 50 hertz, so 314. Then it will be cos omega t, and cos omega t, if we want to represent in terms of sine, then it can be, again, that we have already seen, that it can be represent like sine omega t plus 90-degree. So it will be finally, this value will be finally 326.56, and then it will be sine omega t plus 90-degree. So 326.56, it is this is voltage, so volt. 326.56, it is the measurement of the VL, and this represents that this inductive voltage, a voltage drop only across the inductor, this leads the corresponding current by 90-degree. Now this can be again found or this can be shown in different way, like VL, L di by dt, so it will be L, then I, when we took voltage as reference, then the expression of I that we obtained was Im sine omega t minus 70.5 degree. So here we can write d by dt, and then Im, which has value 5.2, and then sine omega t minus 70.5 degree. So now if we simplify further, then it will be L, the value is again the same value we will be putting 200, then 10 to the power minus 3, 200 millihenry, and then 5.2 will come out of the differentiation as it is constant, and from the rule of differentiation we will be getting again 1 omega here, and that is 314, and when we will divide this, it will become cos omega t minus 70.5 degree. and this value will again give the same value that we have already seen or written in the previous slide. So it will be 326.56, and this will be cos omega t minus 70.5 degree. Now if we want to represent cos omega t in terms of sin omega t, then again what we can do is we can write that as sine 90 omega t plus 90 degree. So cos omega t can be written as omega t plus 90 degree, and this time previously we took current as a reference and then we calculated the VL value or value of VL, and this time we have taken voltage as reference, and with respect to that the expression of current that we have obtained, there we express the current in terms of phase angle. So with respect to that, now we are differentiating. So on cos omega t, that part can be written as sin omega t plus 90 degree, and then we have to incorporate the phase difference also here. So finally it will be 326.56, and then it will be sine omega t plus 19.5 degree, and this is ampere, sorry, this is volt, since we are dealing with voltage, so this is volt. Now previously we got 326.56, the same value, but we expressed as sine omega t plus 90 degree, and what I said, I took current as reference, and then I, with respect to current, I represented VL, and we know for a purely inductor always that phase angle is 90 degree when current has the phase 0 degree, means current we take as reference. But in the second case, when we are finding the same value of VL, we have here obtained the same value 326.56, but here the expression of the sign is different, and that is sine omega t plus 19.5 degree. And here what I said, I took voltage as a reference, then I expressed current in terms of voltage, and there was a phase difference in the expression of current. And now when we are representing VL, we are getting phase angle as 19.5. Basically VL here is expressed with respect to V when I took voltage as reference. So here the phase angle 19.5 degree is not between voltage and corresponding current, rather this phase angle 19.5 degree is between the voltage drop across the inductor and the total voltage V. That means here this measures 19.5 degree. So when I took voltage as a reference and then I express the voltage difference across the inductor, the phase difference was 19.5. This is the phase difference. This is between total voltage and the voltage drop across the inductor. Though here exactly the scale could not be followed, as value wise VL has 10 times more than VC, but here the length of VL and VC that I took is not VL is not 10 times more than VC, and that's why this angle doesn't look like 19.5, but it is 19.5, and this angle is 70.5 degree. Now both the ways it can be represented. Now next, if we obtain or want to obtain the voltage drop across capacitor, then again the same thing, it will be 1 by C, then integration I dt. Now if I take I as reference, then C, in place of C we will be putting the value of the capacitance, which is 500 microfarad, so 10 to the power minus 6, and integration I. Now this time I, if I take as reference, then it will be omega t dt, and this will be 1 by 500 10 to the power minus 6, and the value of this will be Im sin omega t. So value of Im is 5.2 that we have seen earlier, and then sin omega t dt, and after integration it will be 5.2 and then divided by 500 10 to the power minus 6, and since we are integrating sine theta, so here we will have a negative sign, and then this omega value will come in the denominator as per the rule of integration, then it will be 314, the same value, and in place of sine omega t we will write cos omega t, and next this value will give us 12 and this cos omega t can be written as 90 degree minus omega t. So finally it will be, if we take this minus sign inside and if we adjust the sinusoidal term, then it will be omega t minus 90 degree, and since this was voltage, so unit will be volt. So here we can see that the voltage drop across the capacitor, only across the capacitor, will lag the corresponding current by 90 degree angle. So phase difference is here 90 degree. Now similarly, the same thing VC can be found by applying the second approach, and finally the value that we will be getting by applying the second approach, that will be 33.12, and sine term will be sine omega t minus 160.5 degree and this much volt. So here initially by applying the first approach, when we found VC, basically we took current as reference, and with respect to that we represented voltage drop. So here the phase difference is 90 degree, but when we are taking voltage as reference, and with respect to that we are representing first the current, so there we have a phase difference and in the expression, and then with respect to that current expression, if we find the voltage drop across the capacitor, then the expression will be like this. But here this 90 degree is between the current and VC, the voltage drop across the capacitor, but here this 160.5 degree, this phase difference is between the applied voltage or the total voltage V and the voltage drop across the capacitor. So if we go back to the phasor diagram, then this is the angle. This angle is 160.5 degrees, and this is the angle between the total voltage V and the voltage drop across the capacitor. But value wise it is same, it is 33.12, and this much is volt.